All right. So we're going to talk about what is probability. So probability basically means uncertainty. Okay, that's what we are trying to talk about. So let's assume that there is a school and there are three kids who likes to play soccer and seven kids who don't like to play soccer. So you would say the probability of soccer is 3 by 10, 0.3. And if you want to know what's the probability of not playing soccer, then that's going to be 1 minus the probability of playing soccer. So that's going to be 0.7. Very easy, very simple. So basically, when you are flipping a coin, that's uncertain. That's an experiment that you're doing, which you don't know if it will either be a heads or tails. So that basically what it means by an experiment. If it turns out to be heads, then the probability is going to be half. If you talk about, okay, what's the probability of heads, then what we do is we say the probability is going to be 1/4. And the reason is because if we draw the graph or the tree diagram, so we say if we have heads and tails, then we have heads and tails, and then we have heads and tails. So in total, we have four outcomes, and from those four outcomes, only one is the one which satisfies the probability of having heads and heads. So that is basically that. And now we're going to talk about disjoint events. Okay, so events which do not occur simultaneously. Let's assume that we have a school in which we have three players who are playing soccer, there are four players who are playing basketball, and three players who don't play anything. Now the assumption is that a soccer player cannot play basketball. Okay, they can only play one sport. So if you look in the diagram, you'll see that there are three players who are soccer and there are four players in basketball, and these are different players, these are different people. So they don't have any correlation, they don't have any intersection. This is what it means by disjoint, which means that they do not overlap, or that there's nothing which is occurring simultaneously. So if we say, okay, what is the probability of a kid playing soccer or basketball? Then you will say, okay, there are three players who can play soccer, or there are also four players who are also playing basketball. So 3 plus 4 divided by 7. So that's going to be the total. So basically, you could also write it in this format, which is the probability of soccer plus probability of basketball. So when there are disjoint events and you have an or, then basically you will be using, or you can just add them up. Okay, pretty simple, pretty easy. Now if we say, okay, they're no longer disjoint events but now they're joint events, so now let's say that if the probability of wind is zero point 0.7 and the probability of rain is 0.8, and we talk about, okay, what's the probability of wind or rain, then if we add these two up, we'll find that this is not equals to 1. This is actually 1.5, which is greater than 1. And we know for a fact that the probability is going to be equals to 1 and it cannot exceed 1. So did we make a mistake while we were making, or we were forming this equation? The answer is no. The reason is because the wind and rain can occur at the same time. So it's an event which can occur simultaneously. What is an event? Event is, for example, if I say heads, this is an event. Heads tail, this is an event. Okay, so now what do we do? Let's go back to the soccer example, and now let's say that the probability of soccer was 0.6 and the probability of basketball is 0.5. And the question is, can we figure out what is going to be S union B, or S or B, right? The players playing soccer or basketball. Well, the answer is, only with this information you cannot identify, because you don't actually know how many of the players or how many kids are playing soccer and at the same time they're playing basketball. So you need some sort of cardinality or some sort of measure as to telling you how many people are there who are actually playing soccer or they're playing basketball, and the mid part. So now if we say that, okay, if there are six kids who are playing soccer and there are five basketball players, and we know for a fact that there are total 10 kids, that means that there's some sort of intersection which is going on. So we can say, okay, so there's soccer, there's basketball, and there are total 10 kids. If there's six kids over here and five kids over there, then there's some sort of overlap over here, right? So there are two ways as to solving this. One part is like identifying what is this part, what is this part, okay, and then calculating this part. So it's very easy. So if this is 6 and this is 5, so I can do 6 minus 5, so that's 1. And these are sorry um so what I can do over here is, if I take the union of both of them, right? If I take the union, so this is 6 plus 5, right? So let me do it with the shade so you can understand. So I did 6. Okay, I'm doing S union B. Okay, so this is shaded, and then I shade this part. Now what do you find? You find that I counted this part twice, right? So this is also called the inclusion exclusion principle, which is that I will do S plus B minus the intersection part. So in this question, it is, you should be known as to what, how many people are there in the between, or how many people are playing both of the sports, and then you can solve this question. Okay, so what that basically means is that if you take this principle is very general. Okay, you can apply this to joint events as well and disjoint events as well, because if you look over here, what we did was we added the probability of A, we added the probability of B, and then we subtracted the probability which was the intersection, right? But if we look at the disjoint one, there's no similarity. So what tends to happen is that this intersection part becomes 0, and then you will get into the disjoint the disjoint scenario. So you just have to remember one formula, which is this one, and if you remove this part, then this will automatically become the disjoint scenario. Now we're going to be talking about independence. Now, independence is saying that when one event doesn't affect the other event. For example, flipping a coin. But if you flip one coin, it's going to be heads. If you flip the second coin, the first event is not affecting the second event, right? So you say that the two events are independent. Now, if you talk about chess, on the other hand, if there's player one who is playing a certain move, then for the next player, the events are dependent because the first event is affecting the other player's turn. So now one would say, okay, but didn't we do the same thing in disjoint as well, where we said, okay, they're not occurring simultaneously? No, the difference is, in disjoint, we're saying that two events are not occurring at the same time, which means there's no overlap whatsoever. But in independence, we're saying that one event is affecting the other, one event does not affect the other event, and the overlap is possible. Okay. um, so for example, let's say that we have like 100 kids and 50 of them play soccer and the others don't. And what we do is we give you a question, which is you need to randomly select the kids in the two rooms. So how many kids will there be in room number one? Well, you're choosing on random. You might take 50 from soccer, you might take 50 from not soccer, so you'll have like 25 soccer and 25 don't play soccer in each room. So basically there was 100 there was 50 kids who played soccer, and there were 50 kids who did not play soccer, and you had to distribute them in two different rooms. So what you would do is you would pick one from here, put them here, one from here, one from here, and put them there. Ideally, we'll say that maybe you are like selecting like 25, you're doing even selections, you're not doing odd selections. Okay, now if you say that there are 40 soccer and 60 don't, so how are we going to split them in two different rooms? Well, this is going to be a 30-70 split. And the reason why this is going to be a 30-60 split is because you are going to you are what you're basically doing is you're saying, okay, there is 40 soccer players and there are 60 players who don't play. And um, if you're doing like a 30-70 split, then um, you do zero point 0.3 times 40, and then you do zero point 0.7 times 60, right? With that, you'll get that there's 12 players who are playing soccer, and there are 28 players who are who are not playing anything. And then zero point 0.6 is times 30, which is again going to be 18 which don't play soccer, and then zero point 0.6 times 70, that's going to be 42 players who play soccer. So essentially what we are doing over here is we are applying the and operation. Okay, so whenever the events are independent, you multiply their probabilities. Okay, that was the point which we were getting at. Since there were like two rooms over here, the chance of them splitting was 50-50%, right? 50% in one room, 50% in the other room. So we did 50 times zero point 0.5, that was 25 students. 25 students were playing soccer. And then 50 times 0.5, that was 25 people who don't play soccer. Similarly, we did the same thing with this one. We said 40 soccer, 60 don't, and we want to do a 30-70 split. So we did 30% of this, 70% of that, 30% of this, 70% of that for the second room. So that was independence. Now, before I get into what is dependent events, I need to talk about conditional probability. Okay. So over here in independence, we were saying that one event doesn't affect the other event, right? But in conditional probability, we say that what if an event has happened, and now what is the probability of something else occurring? So for example, let's say if today was raining, tomorrow will I bring an umbrella? Or let me make it more clear. If today is raining, what's the probability of me actually taking out my umbrella? It's going to be very high, because if it's raining, then I would want to use an umbrella, right? So this is what conditional probability is. Okay, so um let's say that if I'm tossing a coin, right? I'm tossing it twice, and I have these four scenarios, which is head, 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 tail, tail, head, and tail, tail. And now, if I say what was the probability of heads, heads landing, you would say it's 1/4, because there's one event which is heads, heads out of four scenarios. But what if I say that, okay, I don't want this scenario to occur, or instead, what I want to say is, what if I already tell you that the first head is going to be the what if I told you what's the probability of head, given that the first one is already head? Well, you would say the probability is now half. And the reason why this is going to be half is because now you're just going to look at this scenario, and you're not going to consider the tails at all, because you already know that the first one is head. Since you know that the first one is already head, now you only have two scenarios, and out of which one is the one that satisfies, which is head, head. So you say that the answer is going to be half. So what you're doing is you're saying, or you're writing this in the mathematical format by saying probability of head, head, given the first is already head. So that was basically conditional probability. Another example of your dice is that if I roll a dice twice, what is the probability that the first die has a sum of six, or not the sum of six, but the first one equals to six, and the sum is 10, right? So I would say the probability is 1/36, because you would say, okay, the first one is 6, okay, and the sum being 10 is going to be 1/36. The reason is because you are looking at 6 over here, and you're looking at the sum 10, and you say that this is 1/36, because this is the only probability that you can achieve. But what if now, instead of that, I say, okay, what if it's already given that the first die is going to be 6, so you actually know what it is. So what you do is you isolate this, or what you're doing is you're changing your pool, and you say, okay, instead of my entire grid being the pool, this is only my pool over here, and the pool is going to be this particular row, and from here I also need the answer to be sum as 10. So you'll say, okay, 1 2 3 4 5 6, I have 10 only once, this is going to be 1 by 6. So you get this. The other way as to how you can write this down is you can say, okay, what is the probability of A and B equals to probability of A times the probability of B given A. Okay, so over here, if we say what's the probability of just landing 6, then if you see over here, there's 1 2 3 4 5, sorry, so it's the first die landing 6, so that's going to be 1 by 6, sorry, 6 by 36. What am I doing? Yeah, so this is going to be 6 by, it's going to be 1 by 6. Why did I write 6 by 36? No, there should have been 1 by 6. Anyways, so the first die can be anything, so it's going to be 1 by 6, and we just calculated this part, which is 1 by 6, and when we multiply both of them we get 1 by 36. So you can also calculate it like that as well. So the general product rule is that probability of A and B equals to probability of A given B given A. If they are independent, right, then we would say that this is just going to be probability of B, which is what we were doing earlier over there. So if you see over here, it's the same formula, but this probability B is being substituted over here, right? So the idea of conditional probability is that you're basically adding this sort of like hint, right? We were saying, okay, probability of head um given something, add that part in. So that was conditional probability. So now let's get back to the soccer kids example. Let's say that there were again 50 soccer kids, 50 don't play. Room 1 has how many kids can be fit in room 1? uh, if it can fit 50 kids, and the first room is having the World Cup being shown on the TV, whereas the other doesn't. So you would say, okay, all of the soccer kids are going to go there, right? um, and the reason is because this is a dependent event, because you're saying, okay, since it has a world TV premiere, all of the kids are who like to play soccer are going to go there because they're dependent. Let's take another scenario, and we say, okay, there are 40 kids who like to play soccer, 60 don't. 80% of them likes to wear running shoes. Okay, so how many players or soccer players are going to put on the running shoes? So you will say that zero point 0.4, so there's 40 kids, right, times 80% maximum, so that's going to be 0.34. And the reason why you did this is because you said, okay, S given R, you already know that running shoes are going to be the shoes which the soccer players are going to like. Um, Sorry, because you say over here 80% we're running, 80% of the soccer players are running shoes. So that's the given thing over there. We can also write this in sort of like a tree diagram as well, where we say, okay, we have 40% of the players, soccer players, who are wearing running shoes, so that's S given R, and they're not, so that's going to be S given not R. So what you're doing is you're multiplying zero point 0.4 with uh with the with how much, with zero point 0.8, and then you're getting your probabilities, so 0.32, 0.8, 0.3, 0.3, and these are the probabilities of not or wearing the shoes and not wearing the shoes. So in independent, what you'll find is that if when we were placing these soccer players and not soccer players in different rooms, we had this sort of like division, because these were the room 1 players, these were the room 2 players. Over here, when we were doing it, we had some sort of like biasness, because the running shoes, the players who were wearing running or who were playing soccer were more inclined to wear them, right? Or when they were being placed in the World Cup premiere shop or the room, they were more likely that soccer players would join that. So conditional probability just states that only given that it can occur in independent events as well, and it can also occur in dependent events as well. Okay, so moving on, then we have the random variables, the mean,